Good morning, everyone. First thing, is the live streaming working? Because my two sons are watching at home. So hi, Ethan and Aidan. Quick intro, I'm Kanta Vekaria, my boss, David Rustling, this Linaro CTO, which means I get to be involved in a variety of technologies. The most recent being high-performance computing, HPC. Furthermore, being in the office of the CTO means we have to push the boundaries. So as a result, this is no ordinary talk. So get your devices together, scan the QR code, go to the URL, linaro.co/HPCX. Yes, this talk will be different. Linaro is all about collaboration, and this keynote will involve just that. Now, this is a picture I'd like to take of the audience scanning there. This hasn't been done before at a Connect event, which makes it risky and all that more exciting to do, I say. If you can, scan the code. If you can't, there's a URL. That's the test question. Ooh. As you can see, the results are displayed live, and it seems to be working pretty well so far. I thought as much. There'll be some sleepers. And I know there will also be there'll be a mischievous lot who'd like to try and break this. Please do, but leave it till the end, please. So, right, on to HPC. How many of these do you recognize? Siobhan? Ooh, people are thinking. Don't take too long. Oh, yeah, there was a 0. Where's it gone? I apologize. There was a 0. It's what? First fail. There was a 0. It's gone. I actually had put the 0 there because my children said, what is this? Not bad. I, too, only knew 1. Here we go. So the first one is the ENIAC, or whether it's pronounced ENIAC, I have no idea. Some argue that it wasn't even a supercomputer because it was based on vacuum tubes. The CDC, as some of you may have recognized that one. That CDC was the first to rely on transistors. You all will be familiar with the Apollo guidance computer, but it was the IBM 360 that managed the Apollo 11's operations and management communications back to Earth. The Cray XMP was a predecessor to the Cray 1, so it's not Cray 2, and was the first multiprocessor computer offered by Cray. The Fujitsu Wind Tunnel, now I think that's just the coolest name, was a joint project of the National Aerospace Laboratory and Fujitsu. So that's a bit of a history lesson over. Now, on to the raw processing power. As you can see, the raw processing power of these early supercomputers are now shadowed by the latest everyday and small gadgets of today. A Cray 2 was equivalent to an iPhone that is already, what, 4 or 5 years old? I'm not too sure. I'm not a fangirl of iPhones, so I don't keep up. Right, this slide does go against presentation guidelines of squashing and squeezing, but I really wanted to show this as it shows a comparison of what we have today with smartphones, watches, games console, and early supercomputers. A Sony smartwatch is more powerful than a TCM CM2, and a PlayStation 4 is more powerful than an Intel ASCII Red 1998. Crunch these numbers for a little while because there's a question coming up. So, next question. A Tianhe 2 is number 2 on the top 500 supercomputer list. These are its credentials. How many PlayStation 4s is it equivalent to? Ooh. This is good. Keep going. I'll give you a few more minutes. Shall I put you out of your suspense? It's 18,400. Not bad. People are still going, right? Yeah, yeah. Oh, yeah, yeah. Keep going. Supercomputing has been around for decades and is very much so dominated by Intel. Now, this has not been the first talk on HPC at Linaro Connect. The first was in Bangkok, where we had Eric Heinenefer from ARM Research, and then from CERN at Budapest, along with Chris Adeniyi-Jones, also from ARM, who ran a tutorial on scientific computing. Also, Fujitsu, in collaboration with Riken, shared news on the post-K supercomputer. So yes, Linaro was hinting on things to come. But why AArch64 for HPC? ARM made its first step into HPC on the Mont Blanc project. The Mont Blanc project tackled the initial work of building test systems and porting software for ARM HPC. Since then, and from work involving the US Department of Energy's, the DOE's Fast Forward 2 project, this has demonstrated that AArch64 is competitive on a per-core and per-socket basis. Furthermore, the HPC community was seeking multi-vendor options. They wanted choice. They do not want full proprietary systems which inhibit them from fixing problems they have found in, say, for example, OpenMPI, and relying on the vendor instead. And we know what the lead time for such fixes are. The ARM ecosystem brings choice and better optimized solutions. It also brings the opportunity to co-design and co-develop from architecture design right through to software. With choice, the need for standardization and platform compatibility is paramount. Technology standards such as Gen Z are inspiring the industry, but we must not forget Fortran. Yes, that still matters to HPC. With ARM's introduction of the scalar vector extension as a standard architecture, and the need for massive parallelism means changes to software, it's an opportunity to modernize software, and what better way than open source. These are some of the recent headlines, and they have demonstrated that the HPC community are taking ARM seriously. At the recent ISC 17 conference in Frankfurt, Atos announced the Bull Sequana X1310, an ARM-based variant of the company's Sequana X1000 supercomputer line. Penguin Computing also announced its own ThunderX2 powered cluster platform. The product, known as the Tundra ES Valkyrie, I'm not sure if that's pronounced correctly, can be ordered now and will ship in the third quarter of 2017. HP Enterprise unveiled the Machine, the new memory-driven computer. The GW4 Alliance, together with Cray, will be providing a Tier 2 HPC service named Isambard, after the renowned Victorian engineer Isambard Kingdom Brunel. The aim is to provide multiple advanced architectures within the same system in order to enable evaluation and comparisons across a variety and range of hardware platforms. It's all about choice. So why Linaro? HPC has a large and growing open source component. We can offer tool chains to those who want choice. We can focus engineering on library optimizations that will benefit all microarchitectures. It's a place where SOCs, system vendors, system integrators, users, distros, hyperscalers can co-develop and root the foundational software to make choice easier for the desired application space. From this, the support of members, a special interest group was formed. This was formed under the existing enterprise segment group, LEG. We currently have 7 members: ARM, Cavium, Fujitsu, HiSilicon, Washington, and Qualcomm, and Red Hat. They form the steering committee. We also have CERN and Rikon on board, on the advisory board. They provide subject matter experience and guidance as users. User feedback is important. It's not just about SOC enablement. We need to get user feedback. This will help us drive the engineering in the right direction and ensure that the application space is ready for when silicon lands. We are working towards optimization, standardization, interoperability, modularization, and orchestration. That's a lot of words. We want to lower deployment barriers and management barriers by leveraging the Linaro Developer Cloud and other services to develop cost-effective, cloud-based HPC development frameworks. HPC environments are hard to come by. They're expensive, and the Developer Cloud will provide instances of HPC environments to give access to developers to hardware that they can start developing the applications on. The data-driven economy is a boom. Machine learning and deep learning are both critical to the future of HPC, also mentioned by George yesterday, specifically as a path towards exascale computing. Driving engineering in HPDA and machine learning will aid the success of organizations to fully capitalize these technologies. This slide has got lots of information on there. It gives an idea of the breadth of scope in the HPC SIG. The items in color have been prioritized and is what we are working on at the moment. Note the colors do not signify anything. I've just highlighted those to present what we're working on currently. There really is a lot to do in this space. So to start, we are working on getting ARM enabled on OpenHPC. I'm going to let Renato Golin, who is the tech lead in HPC, talk a little bit about this. Where is Renato?
Thank you. It is. So OpenHPC is it's a package management. It's an external package repository that we have packages that help you set up OpenHPC or HPC clusters. So instead of trying to find which package merges with another package and which component works with another component, we get all of these components and we test them on ARM and other people on Intel, and we make sure that these things work out of the box. And for that, we write recipes and documents that will help you to just follow the guidelines, copy and paste shell commands, and then you have a HPC cluster at the end of it. And in Linaro, we're working to automate these further and then to press a button and have a cluster at the end. The latest release is 1.3.2. We validated this with the ERP kernel in some machines, with the standard CentOS kernel in other machines, all of them ARM, of course. And this is still in tech preview for ARM because some of the things don't work out of the box. So that's one work that Linaro is doing, which is to talk to the communities that will make this be out of the box. And next slide. So if you see at the top left, OpenHPC, we actually have two mentalities about this. One of them is the things that should just work, and the other ones are the things that should just work as well, but you can customize. So for instance, basic infrastructure packages like Werewolf, that they provision the nodes, and Slum and MERS, that they dispatch jobs, and InfiniBand and disks, they should just work. So you run the recipe and you have a cluster at the end with all of these things already installed. You don't really care much how performing because they're really not in the critical path. But then you have all the applications and libraries and tool chains and that you want to use out of the box to see if it works, but you also want to fiddle with it, you want to change components, you want to choose different libraries. So OpenHPC allows you to choose a specific tool chain with a specific MPI implementation as a default, so when you just like compile stuff, you run make, everything works fine. And so that helps us tune specific parts, so you install the whole HPC, OpenHPC, and then you just start fiddling with one library and running benchmarks, etc. This is good for us to fix bugs and make them faster, but it's also good for the users that will then be able to have their own custom version and install a package and recompile from source and apply patches and etc.
Great. Thank you, Renato. So, I figured you're waiting for the next question, so. Have you been involved in deep learning? Ooh. We know that, Mark. As mentioned before, the data-driven economy is in boom. And machine learning and deep learning is making an impact in HPC too. But first, I want to make clear some terminology. And here's a question for you. Machine learning, in simple terms, is programming a machine to then go and learn itself. There are many methods of learning. In supervised learning, oh, it's okay. You could leave it back on that question, it's fine. In supervised learning, the users train the program to generate an answer based on a known and labeled data set. Neural networks use supervised learning, in which inputs and outputs are known, and a goal is to build a representation of a function that will approximate the input to output mapping. In unsupervised machine learning, the algorithms generate answers to unknown and unlabeled data. Reinforcement learning allows the machine or software agent to learn its behavior based on feedback from the environment. This behavior can be learnt once and for all, or keep on adapting as time goes by. This is done through a method of rewarding. Evolutionary algorithms, such as genetic algorithms and genetic programming, allow you to explore a space of parameters to find solutions. It's a landscape of solutions that score well according to a fitness function. Solutions are encoded and pitted against one another in a manner comparable to natural selection, where the best solutions survive to cross over and produce new solutions for evaluation. So how does this fit with HPC? HPC was traditionally used by researchers for simulations, and well, machine learning really took off once we realized GPUs were great at executing machine learning techniques. And we started to see real results very quickly as well. HPC offers the opportunity to accelerate performance and deepen understanding of large data sets through machine learning, through parallelism, and methods of exploiting data parallelism. This will allow training of models over larger data sets and over quicker iterations. We are now at a point where we consider supercomputers designed for both computational science as well as machine learning. So it seems that we do have a fair few in the audience who have been involved in deep learning. That's really good, and I'd like to see that within the next few Connects we have more and more people who are involved. So, next question. Yes. Great. Yes. Who's that one? Was that you, Mark? Is that Maxime? No. I'll have a word with you later. So, Siobhan, leave that question up, but we'll go on to the next slide. Leave that one there. So, what about artificial intelligence? For me, yes, the AI term is being diluted. I'm a purist, I'm a traditionalist. And therefore, true AI means replicating many aspects of human intelligence and become an entity on its own right. Tesla's theorem, intelligence is what machines haven't done yet. Note, if you Google Tesla's theorem on the internet, it will come up as AI is something that hasn't been done yet. That's not quite right. He's been misquoted several occasions, and he's tried to rectify that. But as we know with the internet, once it's out there, it's gone. There's nothing you can do about it. There's so much more that needs to be untapped and solved before we could say we have reached true AI. There is emotional intelligence, social intelligence, to name a few. The fundamentals of human intelligence is self-preservation. Is that what we want in AI? We have to ask ourselves. Machine learning algorithms take time to get right too. Those that are out there have issues too. Here is one example of many from Google, where they designed a neural network that thought dumbbells looked like that, with an arm to go with it. It could not determine that actually that's an arm and that's a dumbbell. It failed to completely distinguish that. So coming back to HPC, with a data-driven economy, HPC is no longer an exclusive domain for science labs, but it's becoming mainstream. HPC brings the benefits of advanced algorithms to users at scale. Data centers will also have HPC environments. But then HPC environments are expensive, and to make them more accessible, there are now many HPC cloud service providers. But these come at a cost too. And as a result, we explore containers. Containers work on bare metal, and clouds provide flexibility in management of workloads. They allow for a varied setup for different applications. They make migration to newer software versions easier and less impact on production systems. With these new approaches, we have to consider where the data lives. For scientific computing, on the other hand, petaflops was yesterday's news. There is a big movement to exascale computing, exaflops. With that comes challenges also. What architecture is going to cut it? As a result, some of the research labs are looking for co-design. How do we scale? Simply scaling from today's requirements for a petaflop computer, the exaflop in 2020 would require 200 megawatts. That doesn't scale. Memory bandwidth and capacity are not keeping pace with the increase in flops. Decreasing clock frequencies to conserve power will mean the number of processing units on a single chip will have to increase. This means exascale architectures will likely be highly concurrent. The cost of data movement is also very high and needs to be minimized. And then there's always, what about compilers, the changes that will be required to support this in compilers? Which leads us to another realm, quantum computing. Paul Benioff first applied quantum theory to computers in 1981. They work on the qubit, which unlike traditional computers who focus on binary 0 and 1s, the qubit focuses on 0 or 1 and on both simultaneously. It has a state where it can be in both states. The notion is that a qubit represents subatomic particles that have a superposition state also. They say that this will potentially be millions of times more powerful than current supercomputers. And at one point, quantum computers would replace silicon chips. D-Wave have already created a quantum computer, and I've provided a link. The chip in the slide set is from the D-Wave quantum computer. We saw this in ICS, and it just looks beautiful. I've also provided some recent headlines that were publicized around quantum computing. IBM makes a breakthrough in quantum computing. And the second one is a bit of a clickbait. Scientists try to speed up the internet with, yeah, right. But there is good information in that slide. It is a very exciting space. And I have to ask myself, could quantum get us true AI? So I pose that question to you. Will we ever get true AI? Leave that question up. So this is a call of those who would like to develop and take part in the HPC engineering that Linaro is working in. There are some links here. ARM have a good repo. There is a link to the developer cloud where we are setting up HPC instances. There's a link to the Open HPC project. They have an abundant amount of issues, and we could do with help for anyone who wants to participate. It's an open project. Anyone can participate. Also on GitHub, there's a whole repo on machine learning for those who want to dabble in deep learning, machine learning techniques. And there are also talks today, which are very related to HPC. There's a RAS talk on ARM64. And tomorrow, there's a talk on vector optimizations for glibc, benchmarking in the toolchain working group. On Thursday is the data center day, so we are running a HPC BOF where we're focusing on what is required to make HPC development easy and what are the obstacles we need to overcome. Also on Thursday, we have Riken presenting an overview of the post-K supercomputer. And on Friday, there's a talk on deep learning on ARM platforms. So do join in. If you are interested and feel you have a side project and would like to just engage, just please speak to Renato or myself, and we can direct you accordingly. On that note, thank you. I'm glad the poll seemed to work. And it was 50-50 about whether we will get true AI. That's interesting. Thank you.
Thanks very much, Kanta. That was very interesting. And very much looking forward to Linaro getting more involved in this exciting area. I'm now very pleased to welcome Nishiguchi-san, who is the chairman and CEO of SocioNext. He's going to talk about some products that SocioNext have been working on, and then after he has talked, we're going to show you some exciting new products. Thank you.
Good morning, gentlemen. Sorry, I cannot speak English so well, so that I need interpreter, please. 今ご紹介いただきました西口でございます。少し私の会社について、紹介をさせていただきたいと思います。
Let me introduce our company, SocioNext.
SocioNext は富士通、パナソニック両社のシステム LSI 部門がカーブアウトされ、作りました会社です。
SocioNext is the company carved out from the Fujitsu and Panasonic.
我々SOC の開発、ファブレスですから製造はすべてアウトソースですけれども、そこで製造したものを販売するという、それを事業にしています。
Our business is mainly for the SoC design and we outsource all the manufacturing.
約2800人のメンバーですけども、80% が SOC のデザインエンジニアです。
We have about 2,800 employees, and 80% of them are SOC design engineers.
これはあまり必要ないかもしれませんけども、
It's not really necessary though.
私は京セラという会社で、社長を終え、その後今のような会社の指導を引き受けました。
I have finished my career as a president of Kyocera and now joining this company.
この絵はソーシャルネクストとしてどういうマーケットにこの SOC 事業を展開するかということを表した絵です。
This is the picture showing as Socionext which market to be approached.
一つはこの IoT 分野に展開していきたいということで進めております。
First of all, IoT market is the target applications.
我々は3つのコア技術を持っております。
We have three major core technologies.
一つはイメージングのテクノロジーです。
First one is the imaging.
あとは高速の ADC また DAC を軸にしたネットワーキングのテクノロジーです。
Next is the networking technology based on our high-speed ADC and DAC.
3つ目は高性能また高密度実装によるコンピューティングのテクノロジーです。
Third one is the computing technology based on the high performance and the high density packaging technologies.
これらのテクノロジーを用いて、汎用の ASSP からカスタム SOC まで、特に最終製品を考慮した最適な設計を行うということを行っております。
By utilizing those from the standard ASSP to the custom SOC, with consideration of the final products, we design the SOCs.
もうすでに表してますけれども、この赤くマーキングしたところは IoT 端末としてのカテゴリーです。
This red marked category is the IoT devices.
各信号に対応するセンサーとコンピューティングの組み合わせで実験しております。多くの商品にARM コアを採用しています。
We deploy many ARM cores on many products.
センサー
with the combination of the sensors from the IoT devices and computing.
もう少しコンピューティング処理を強化することでエッジアプリケーションに対応しております。
Enhancing the computing power, we also support edge applications.
ボゾーキャスティングのような多チャンネル対応や RF 技術を応用したサテライト通信、また映像からのメタデータ抽出を実現しております。
The networking applications and also satellite broadcasting utilizing RF technologies, and also the which one is metadata processing, taking the data from the imaging.
これはクラウドに関するグリーンの丸をつけたものですけれども、当社が保有するこのスケーラブルなこのコンピューティングを実現する技術によりまして、クラウドへの参入も図っております。
Greenmark is the cloud application, violet color. It's the cloud applications by utilizing our scalable technologies. いいです。
従来から公表いただいております、高速ネットワーク通信デバイスは、データセンター間通信にも利用していただいています。
The data center to data center communication, our networking technology is being selected by the many customers.
当社が開発したマルチコア CPU です。
This is the multiple CPU that we have developed.
レトロコアとして、知られていますコーテックスの A の53を24個配置しました。
We use the 24 cores of Cortex A53, which is known as a little core.
あえて動作周波数を 1GHz に抑えております。
We intentionally save the clock frequency at 1 GHz.
効果として、消費電力を大きく抑えることができ、5W を達成しております。
By the result, we could achieve the very low power consumption at 5W.
これは先ほど示しました特に IoT のマーケットでは必要だと我々考えています。
This is we believe it's very mandatory for the IoT devices that we have explained.
コアを接続するバスのスピード、そしてバスにつながる DDR のスピードを考慮した絶対設計が求められます。
The entire chip design is necessary to consider the balancing, the connecting the core and the bus, and also bus and the DDR.
当社はSoC 設計の経験から、チップ全体をベストなバランスに仕上げております。
We make the best balance in the design through all the experience of the ARM SoC design.
IoT 端末は先ほど申し上げたように非常に低消費電力ともう一つは低レイテンシーのバランスが必要です。
For the IoT devices, we need to consider the balance of the low power consumption and the latency.
我々このチップをシンクエサーと呼んでいますけれども、シンクエサーは24個のコアと DDR4 の組み合わせによって実現しております。
We call our product Synquesa. This chip achieved both of them by utilizing the combination of the 24 cores and DDR4.
エッジではIoT 端末情報を集約するゲートウェイという機能とクラウドで処理するプログラム一部をオフロードする機能の2つの処理が行われます。
We consider two use cases on edge devices. One is the IoT gateway collecting all the signals from the IoT devices, and the other one is the offload engine from the cloud computing.
当社はマルチコアを生かした IoT ゲートウェイを提案します。
We offer the IoT gateway utilizing multi-cores.
これは次ページで説明したいと思います。
I will explain that in next page.
また、オフロード処理は後で述べますソシオネクス DDT により実現できます。
The offload engine can be performed utilizing the Socionext DDT, which I will explain later.
低いレイテンシーよりもスロープットが重要視されますクラウドはスケールアウトによります分散処理が最も適した領域でございます。
On the cloud side, throughput will become more important rather than latency. We will achieve such a parallel computing by the scaling out.
当社は他社が実現できないレベルのスケーラビリティを提案したいと考えています。
We propose the level of the scalability which nobody can achieve so far.
これは IoT ゲートウェイの活用例です。
This is the example of the use case of IoT gateway.
IoT 端末の信号は ビーコンのような軽いものから映像データのように常時負荷のかかるようなものまで様々です。
The signal from the IoT devices varies from like a beacon as a small signal to the video streaming as a large size signal keep the computing load all the time.
マルチコア CPU はオペレーションシステムのマルチスレッド機能を有効化することで負荷に応じたコア数を割り当てることができます。
By enabling the multi-threading function and the operating system, the multi-core CPU can allocate the number of the CPU according to the load.
多くの端末を一括で集約するゲートウェイにマルチコアは有効なハードウェアになります。
Multi-core CPU will be very effective hardware to gathering all the signals from the many IoT devices.
当社では一つの例としてこのシンクエサを利用した監視カメラソリューションを提案しております。
We are offering the surveillance camera solutions using the Sync-Questa CPU.
もう一つはシンクエサクロスでございます。
The other device is the Sync-Questa Cross.
ソシオネクス DDT テクノロジーを搭載しております。
It has a SocioneX DDT technology inside.
DDT とはダイレクトデータトランザクションを意味します。
DDT stands for Direct Data Transaction.
CPU 間接続をサーバー間接続と置き換えた場合、皆さんはどうされますか？
What do you do if we consider the CPU to CPU connection as a server to server connection?
まずイーサネットが候補となり、インフィニバンドという選択肢もあります。
I think the first choice would be Ethernet, and also InfiniBand will be the next choice.
40ギガイーサネットを選ばれるケースが大多数と我々は理解しております。
Our understanding, the first candidate would be 40G Ethernet in these days.
では、40ギガイーサネットの実行通信レートはいくらになるでしょうか？
And what will be the effective transmission rate on 40G Ethernet?
通信プロトコルのオーバーヘッドにより実質数ギガBPS になっているはずです。
There will be several gigabps because of the transmission protocol overhead.
当社はこのシンクエスタスイッチを活用することによってオーバーヘッドを廃止して10ギガ BPS の実行レートを実現しております。
We removed all the overhead of the transmission protocol and we achieved the 10 gig BPS as effective rate.
これはソーシャルネクスト DDT を利用したスケーラブルなサーバーの例でございます。
This is the example of the scalable server utilizing SocioneX DDT.
この絵のように合計64台の CPU がつながっております。
Total 64 CPU cards are connected as shown in the picture.
Hadoop のような分散処理プラットフォーム上で動作させますと、各 CPU がローカルで処理をした結果を相互参照、また相互結合することができます。
On the parallel computing platform like Hadoop, the result of the CPU calculation can be referred each other or can be joined each other.
Hadoop の弱点である通信ボトルネックを最小限に抑えるソリューションになります。
This will be the solution to minimize the bottleneck of the data networking, which is the weak point of the Hadoop.
本日のこの会場の前のところで、当社ブースでデモをしておりますので、ぜひご覧ください。
We prepared the demonstration at the table in front of this room.
開発中の技術についても少し触れておきたいと思います。
I will touch on the new technology which is under development. スライドを変えた方がいいかな。
ソシオネクス DDT を拡張する DDT レボリューションでございます。
This is the DDT revolution, which is the enhancement version of Socionex DDT.
ソシオネクス DDT で一括処理できるデータサイズはローカルストレージ ×64 でございます。
The data amount that can be processed at the same time, the maximum size is the 60 times of the local storage.
仮に 1TB の SD を使用しますと合計64 TB になります。
If we deploy 1 terabyte local SSD on each local CPU, then total will be 64 terabyte.
これを十分と考えるかどうかは実際にデータを抱えておられるオーナー企業によります。
It depends on the data owner companies to judge if this size is enough.
当社はさらにビッグデータ処理を希望されるユーザーさんのために現在は100ペタバイトを超えるデータを分散処理するためのマルチポート DDT-R スイッチを開発しております。
We made a judge to make it enhanced to up to 100 petabyte to support the potential customers.
ビッグデータの処理が有効となるアプリケーションとして Hadoop を利用したケースを紹介したいと思います。
I will introduce the example on the Hadoop based applications which is effective on the big data.
ソシオネクス DDT の効果は CPU 間の高速通信です。
The effect of the Socionex DDT is the high-speed CPU to CPU connections.
このデータのように処理データが大きくなるほど効果が明確になります。
The effect will be even clear at the bigger data.
10テラバイトのテラ相当処理時間は3時間以内で済みます。
The TerraSort result on 10 terabyte was under 3 hours.
これはクラウドで IA サーバーを4台接続した場合と比較して、約3分の1の時間で処理はできるという結果です。
This execution time under 3 hours is actually the 1/3 of the score which we can take from the cloud service connecting the 4 of IA servers.
AI アプリケーションにも分散処理が非常に有効です。
The parallel computing is also effective on the AI applications.
ディープラーニングのフレームワークの一つであるチェイナーを用いてCPU 数に応じて処理を分散できることをこのように実証しております。
We have confirmed the effectiveness of the parallel computing by using the framework we picked the China.
以上のようにシンクエサは単独使用からスケールアウトによる大規模システムまで幅広い市場に使っていただけます。
Sync-Tracer can be used for the single use case up to big systems.
今一番ホットな市場にクールなソリューションを提供していきたいと考えています。
We're considering to offer the cool solution into the hottest market.
本日のメイントピックスです。
This is the main topic of today.
Linaro、ギガバイト、ソーシャルネクスの3社は シンクエサーをメイン CPU に搭載した標準開発キットをリリースします。
The Linaro Gigabyte and Sociones, we released the standard development kit using Syncreaser as the main CPU.
ついに ARMv8 64ビットマルチコア環境が整いました。
At last, we have an environment to use the ARMv8 64-bit multi-core.
他社の CPU で開発しリコンパイルされてました皆さんお待たせしました。
Thank you for waiting to all the developers who needed to use the different CPU and recompile again.
これに対する詳細説明はまた紹介はリナの CEO からしていただくということになっております。
The detail of the explanation of the Linaro box will be done by the CEO George Linaro.
Thank you very much.
Thank you. これ一緒にここで見ましょう。
So, thank you very much. I'd like to welcome up Martin to the stage. Martin heads up the Linaro Enterprise Group, and he's going to introduce the team who've been working on this. Martin.
All right, so there's a couple people that worked very hard to get this running. Art Bouchard is one. Where do I have Leif, Daniel, Yang? There's probably about 15 people inside of Linaro that worked on this, and there's probably about 30 people at Socionext who helped work on this, and then everybody for Gigabyte. Titan flew with 2 of these last Thursday. He grabbed them off the production line, flew them here, and then we did a sprint. So I'm actually going to have Ard do a bit of a demo. Do you want Ganesh up here as well? Yep. Okay. All right. So. Yep. So you should be able to boot.
So the U-boot thing in the slides you just saw is not entirely accurate. There's no U-boot in this box. We're using UEFI instead. So basically what I'm showing you here is that it just boots like a normal system rather than having to get out your soldering iron and your serial cable, which is quite an improvement over, well, what we're used to. No, not that one.
And this is a PCIe graphics card, right?
Yeah. So actually that's the demo that I'm doing. It's just your desktop and you can develop on it and use it like an ordinary system, which is quite an improvement for many of us. So.
All right, so part of this is that we want you to use this as your desktop. The other part is we really want you to develop software on this, right? So we've got one we've got set up with the graphics card. So one with the graphics card, and then we've got another one that's set up as your develop box that you're going to have on your desk or in your cupboard or wherever you're going to put it. And so what we'll do is we'll go in. Actually, can you do a systop on this one in a different terminal as well? But so typically what you do is you'd SSH in. So that's systop with YouTube, so you can see all the cores. Well, you can see most of them. But there's 24 of them, which is pretty cool. It does take DDR4 memory, so that's also pretty neat. Yep. All right, so Ganesh, do you want to come up and, what do you need, Art? Oh, okay. All right. This is a demo, so, and we only got this working this morning, so. While we're waiting for that, anybody got any initial questions? Where can you buy one? We're going to announce that through 96 boards. So that's where you can buy one. What's that? Oh, okay, all right. So look, the idea is you do it two ways, right? You have that and you use it as your desktop box, or you just use it headless, and then you can do whatever you'd like to do, Hadoop, build your kernel. How long does a kernel build take, Leif or Art, on this thing? How long did, oh, okay. Under 10 minutes is what I'm told, so it's not bad. These are NVIDIA graphic card with the Nuvo driver. The UEFI is the emulated one that we're using. So we'll post what we've done. Any other questions around this? What's that? No, but Socionext has a fantastic server that can do that, where you can have 64 of these things all connected, right? But for this, this is a 96 boards. It's one socket. DT or ACPI, you have your choice. So we're working on both. But for it to meet some specifications that we have around SBSA and SBBR, it's UEFI and ACPI. Device tree is also available. Mm-hmm. Pricing info, much better than you expect. So I think what we're looking yeah. I think what we're looking at for a complete system, box, memory, disk, which you just go buy, it's going to be under $1,000. And we're also looking at just for you to be able to go and buy a board, and then you go and get your DDR memory, whatever, from Amazon and do that. What is the I/O in it? Yeah, no. So it's just standard SATA. The goal of this is for you to be able to get something, order things that you expect that'll just work on an x86 box, and put it in there, right? So you have your SSD. You can use, NVMe with a PCIe card. Yeah, just standard stuff. Yeah, specs are on the web. What's that? Yeah, so there you go. 4 USB 3 and 2 SATA. With the PCIe add-on card, right? But 1 gig. Once we test it, yes. These just rolled off the production line Thursday, okay? All right, so if I could, for all the engineers that worked on this at Socionext, at Gigabyte, and at Linaro, can you all give them a round of applause?
Do you take MasterCard? I'm serious. I'm ready to buy right now.
We'll get you one of the first ones, Mad Dog. Do you want to just pass on to you?
All right, that was really terrific. I think we had a really great morning. So if you received an invite for tonight for the committee dinners, please accept or decline it, either way, so that we know. And then there's one scheduling. There's a lot of automotive sessions going on this week, as you would expect, and so there's one adjustment to that schedule, and I'm going to let Vicki tell you what the details are.
Hi. So as Joe said, we have an automotive track today, and I just wanted to clarify because some of the titles weren't correct. The first